I am Zhang, and I am the first year PhD student from UIUC. And today I will introduce our work DiffSmooth. And I will first introduce some background about adversarial attack first, but I guess many of you may know about it before. It just means that if we add an imperceptible perturbation into the image, and then it will cause a misclassification of the underlying neural network. So nowadays, more and more researchers are more focused on the certified robustness instead. In other words, we are more interested in such problem. Given the input X, a basic classifier F, and the radius R, we wanted to report whether there exists a perturbation delta within some radius that can cause the misclassification of the classifier F. And Cohen later proposed that we can actually construct a new smoothed classifier G, which can be seen as a smoothed version of the basic classifier F with Gaussian distribution. And they show that with this smoothed classifier G, if we know the corresponding lower bound probability PA for the top class CA, then we can guarantee the smoothed classifier G will be robust around the X within such radius. And as we can see, with a larger lower bound probability, we can certify a larger radius. However, with randomized smoothing, we can see that we have to train the basic classifier with Gaussian augmentation. So in fact, we need to train more models in practice, and the cleaning accuracy will also drop a bit. So later, Sellman proposed that actually we can attach a constant trained denoiser, and we can use such denoiser to purify the noise image first, and then use off-the-shelf standard clean image classifier to do the prediction for the purified image. In this way, we do not need to train any new prediction models, and the clean accuracy will also be maintained in a high level. And later, Carnegie proposed diffusion denoising smoothing. It's just proposed a better denoiser, which is DDPM here. So an interesting question is that what can we expect from a perfect denoiser? What if the d theta is quite perfect here? It just means for every epsilon sampled from the Gaussian distribution, we can always recover the noise image. We can always recover the original clean image X from the noise images. And so the corresponding prediction will be all similar with Fx. So the corresponding lower bound for the PA will approximate 1. So the corresponding certified radius R should be quite large. However, when we track the corresponding experimental result for this method, we will observe that the certified accuracy on the large perturbation radius actually decreases quickly in practice. So it just means the denoiser is not so perfect even with the DDPM. So first, another question is that what can we expect from an imperfect denoiser? So first, we prove the theory 1, which just means the distance between the continuous denoising example and the clean input image X is mainly bounded by the magnitude of the perturbation. And second, we first prove that the distance between the one-shot denoising output and the expectation of the continuous denoising sample is mainly bounded by the training noise. And also, as you can see here, the coefficient is quite complicated here, but in practice, it is usually smaller than 1. So by combining these two equations, we can conclude that the one-shot purified adversarial images are within a quite small bounded neighborhood of the original clean image with high probability. So based on this theorem, we can here comes our pipeline. This one is for the standard smoothing. We just use the majority fault around X for the final prediction. And here is the denoising smoothing. The difference is just we will map the noise image X plus delta into a recovery region. And instead, we will use the majority fault inside the recovery region as a final prediction. However, the key observation here is that if we know the recovery region here, why don't we do a second smoothing here? If we do a second smoothing here, as I show here, we just smooth the X, assume the X hat is a purified image, and we smooth the X hat again with another Gaussian distribution. Then we can correct all the misclassified images here. And thus, all the images all purified images inside the recovery region can be predicted correctly. So in this way, we can expect a higher PA and thus a higher certified radius. So formally, originally for a given epsilon sample from Gaussian distribution, and this formulation is for the denoise smoothing. And what we did is that we can first smooth the x hat here with another distribution. And so since we need a second smoothing here, so we still require the base classifier to be trained with Gaussian augmentation. But the difference is that we do not need to use a model trained on the sigma here. Instead, we can just use another model trained on the sigma prime, and the sigma prime is much smaller than sigma. So in this fact, the clean accuracy will also be higher. And in practice, we just use M fixed sampled epsilon prime for approximate the expectation here. So here is our corresponding result of the CIFAR 10. As we can see, as I said before, if we directly use a diffusion denoise smoothing, the certified accuracy on the large perturbation radius will be quite small. However, with the simple local smoothing, but still with the Gaussian trained models, we can not only have a better clean accuracy, but we still can maintain a high-level certified accuracy on the large radius. And it is similar, and the result is similar on ImageNet. As you can see, with a VIT model, if with local smoothing, we can achieve about at least 10% improvement on ImageNet, and we still maintain a higher certified accuracy on the large radius. So it is quite amazing with such simple trick. So another interesting ablation study is about the number of the local smoothing we used. And as I show here, with more local smoothing noise, we can achieve much higher certified accuracy. And if we focus our attention on the larger perturbation radius, we can see the certified accuracy is at least improved with about 10%, 10 to 20%. And the reason is quite simple, since as we've seen before, the inverse of the standard Gaussian CDF is convex. So with only a small improvement on the probability, we can achieve a much higher value, and thus which will lead to a much higher certified accuracy. And someone may wonder if we use more local smoothing noise, then the certification may take more time. But actually, it is not the case. I have shown the time cost of certification on ImageNet with ResNet 50 here. As you can see, even with 21 local smoothing noise, the certification time only improved about 100 seconds. Actually, as I show here, the time for denoising actually dominates the certification time, but the time for local smoothing only takes a smaller part. So someone may also wonder if we control the same computing cost, what the final result will be. And I still show here, even with the same computing cost, like I set the N here to be 10,000 or 100,000, and still we can achieve much better performance even with the model simply trained with Gaussian augmentation. And as you can see, the improvement is not trivial here. It's about 10 to 20% improvement. And still, the result is also similar in ImageNet. Still, let's focus on the simple model with the Gaussian augmentation. Still, we can achieve about 10% with ResNet 50 and about 5 to 10% on VIT. So this result is not trivial, and it's not trivial. So in summary, in our work, we first proved the purified adversarial instance of diffusion model are within the bounded neighborhood of the original clean instance with high probability. And the distance is related on the magnitude of the adversarial perturbation and the data density. And then based on this theory, we propose an effective and certifiable robust pipeline for smooth classifier, DiffSmooth via denoising and log smoothing. And we show that naively combining diffusion models with smooth models cannot effectively improve their certified robustness. So the local smoothing is quite crucial here. And finally, and of course, we achieve the SOTA-certified accuracy on both CIFAR10 and ImageNet. And for the future work, there is one interesting factor we can consider here is that if we have a better diffusion model, then the recovered region will be shrinked. Then with local smoothing, we can guarantee the PL will be more approximate to 1, and the corresponding certified accuracy will be much higher. And another thing to consider here is for the axon here. Actually, we still use the Gaussian augmentation for the additional smoothing, but actually there is no need to be Gaussian for this epsilon prime here. So maybe we can consider another distribution, like a uniform distribution and a Laplace distribution. It may provide a much better performance. And the second thing here is the sigma prime here. In our paper, we usually will set it to the half of sigma here. But in practice, we can set it to a lower level. If that's the case, then we can improve the cleaning accuracy much better. But we still can boost the consistency of the prediction here, which will lead to a higher certified radius. Yes, that's all my presentation. Thanks.